Stop. Stop.
Okay, welcome back, everybody. Again, we're studying physical oceanography, and starting from a fluid mechanics sort of point of view. And so the first couple lectures are basically entirely focused on on mathematics review. See, I said, is this the right class on the first day, but then I think on the second day. So last time, this is basically a summary of sort of what we reviewed. We also went over the syllabus. And so we said, the Earth is a sphere. So we might think, and in many applications you do, use spherical coordinates to discuss atmosphere-ocean dynamics. But this course is not focused on global phenomena. It's focused more on like local, regional phenomena. So we don't need to use spherical coordinates for us. We can think of the Earth as just being flat, and Cartesian coordinates are fine. So we're going to use normal XYZ coordinates. And there's an interesting quirk of oceanography that's a little bit different from most areas of physics, which is that we'll mostly be dealing with negative values of Z, because what we always define is that Z equals 0 is the ocean surface, and then beneath that we have Z less than 0, so if say Z equals minus 10 meters, that would be 10 meters depth. And then when we talk about Z greater than 0, which we sometimes will talk about because the winds drive the ocean and that sort of thing, that's in the atmosphere. We just introduced some notation for vectors. On the board I use these half vector arrows to indicate that something is a vector quantity. We define the dot product and the magnitude. In the notes, just as a reminder, I don't use that vector arrow, I use boldface font, so if you look at the notes, boldface means a vector. And then we talked about generalizing from the idea of a single vector to vector fields. And so a vector field mathematically it's a function that tells you at any given point in space what the relevant vector is. And so we talked about, for example, the velocity vector field. So this is one we're going to talk about over and over in this course. And you can think about it as if you have the air in this room, the air is sort of moving around a little bit. And so if we could measure very accurately, we'd say at every point in this room, the air is moving a tiny bit in different directions. And so that would be a vector field, the velocity at every point in space. And those vector fields are often also functions of time. So it assigns a vector to every spatial location, and then that vector field might be different at every moment we measure. So it depends on the free space dimensions and on time. And we'll talk about vector fields both in 2D, generally in the XY plane, which that's east-west and north-south, inclusive horizontal and meridional. And also then in 3D, where we add the Z up-down direction as well. Just quickly review calculus concepts. So we're all, of course, familiar with the definition of the derivative for a function of a single variable. Because we have three spatial dimensions and time, we're going to be using partial derivatives much more often than traditional single variable derivatives. So we use this different symbol, the curly D. And how we take a partial derivative is just the exact same way, using the same normal rules like power law rules, chain rule, quotient rule, etc. That we usually do for a variable, a single variable. When you take a partial derivative, you just essentially say every variable that you're not differentiating with respect to is just considered frozen. So if you're taking d by dx, for example, any y's or z's or t's or anything in your expression, you just treat those as constants. And then the last topic, which we're going to pick up again today, is Taylor's theorem. And so we're going to use Taylor's theorem over and over in the next few classes especially to derive the laws of fluid mechanics from the basic ideas of Newtonian mechanics. Things like we're basically going to start with F equals ma, apply that to a little bit of fluid, do a bunch of Taylor series approximations, and then we'll end up with the Navier-Stokes equation. So we're going to use this over and over. And the Taylor's theorem expresses the idea that I think is it's intuitive, I think, to many people, that if you have some kind of complicated function, well, this is not my correct marker. You have some function, and it has arbitrary behavior. But any point we look at it, if we zoomed in more and more, if we zoomed this out and had like an inset, it would basically look like just a very weak curvature. And then if we zoomed in even more, it would look almost exactly like a straight line. You can do that on any kind of computer plot. You zoom in enough, and everything is a straight line. We'll talk exactly about what that straight line is. That's what Taylor's theorem tells us. It says if we're given a function, how do we know what linear function is going to be the best approximation local to some particular point? So obviously you can't approximate this function as a straight line, as one straight line that applies to all points. I mean, you could, but it'd be a terrible job. You could fit a line through it like that if you're doing something like least squares. But what we mean by Taylor's series is that every point has a linear approximation, and these get infinitely accurate as we get closer and closer to the base point where we're making our Taylor series around. Okay, so today we're going to continue with our mathematical review. And a lot of it is going to be focused on this Taylor's theorem, but moving from a single dimension, so a single variable we talked about last time, into multivariable cases, and then putting it into vector language. And so we'll start to see vector calculus concepts, such as the gradient, come in today, and all that stuff will be defined explicitly. Okay, does anyone have any questions about the review or anything else before we get started? Okay, well, feel free to pipe up at any moment if you want to have any questions. Okay, so let's go back to Taylor's theorem. So last time, we wrote the theorem as, for any function f of x plus delta x, we should write x naught, is equal to f of x naught, that's the value at our base point, plus delta x times df dx. And that derivative, we always evaluate that at the base point. And then last time we wrote some other terms, but this time we're not going to go any further than the linear level, because we won't need anything more than that. Plus this extra term, this error term, they call it, that's proportional to delta x squared. And so then just as a reminder, we're basically always thinking in the limit that the delta x becomes extremely small. And so what that means is that we have this term here is called zeroth order. So it does not depend on delta x, or if you wanted, you could say this depends on delta x to the power 0, which is 1, right? So this term is zeroth order. This term here we call first order because delta x appears to linear to the first power here. Now all the other terms are delta x squared or delta x cubed or higher and higher powers. And then when delta x is a number that's much smaller than 1, when you take higher and higher powers, those things get smaller and smaller. Like a tenth goes to 1 over 100, 1 over 1,000, etc. So all these terms, we're always just going to sort of ignore them. But if we want to put an equal sign here, we have to say that they're actually there. Otherwise, we would have to make it approximately equal. Okay, so I'm just going to do a little demonstration here that sort of makes really concrete the meaning of the first order Taylor series, which is just f of x is approximately equal to f of x naught plus delta x. And here's our derivative. So now we're just going to say approximately equal. We're going to drop this error term. And so what is the interpretation of this? We can make that really concrete. So let's do an example. So consider some complicated function. Such as f of x equals, what did I use some particular gross example? Yeah, okay. So the example I used in the notes was sine of x squared plus 10 e to the minus x plus log of x plus 1 all squared. So this is just, it has no physical meaning that I'm aware of, just some function that's just a bunch of terms that don't add together nicely. And so if you encountered this kind of function from some physical problem, it would be an unpleasant experience because it's awkward in 3 terms, and also it has poles here. So when x equals minus 1, this thing goes to infinity. So it doesn't have good behavior everywhere, etc. And so the This function looks, so -1, we've got a vertical asymptote, and it looks something like that. So if but let's say we are interested in doing some kind of physical calculation involving this function, but we really care about the behavior in the vicinity of some value of x naught. I'm just going to pick the value 4. So just for whatever reason, the physics we're interested in is near this value of x naught equals 4. So we really don't need to deal with the whole complexity of this function. We don't care about what's happening at x equals -1 if, say, all of our physical regime is just going to be happening within some little neighborhood of x naught equals 4. So what we would like to do is make a simplification of this function. So for example, make a linear approximation, which is what we're going to do, that is very accurate near x naught equals 4. And that way we can just work with that linear formula and not be troubled by all the sort of potential difficulties that arise with this complicated formula. So let's try to fit f of x to a linear function near x equals x naught. I'm just going to choose the value 4. So what we mean by a linear function, we all remember the classic formula, high school formula for the straight line is y equals mx plus b. And so I'm going to say our approximated function, so we're going to say g of x approximates f of x near x equals x naught. And we're going to define g of x as equal to m times x plus b. And we want to find m and find b. So we want to just take our complicated function and say, well, when we zoom in enough, we know it's going to be a straight line. So let's figure out what is the best straight line to approximate the function at this particular point, just starting from the idea of sort of modeling. So not invoking any particular theorem, but just saying we want a line. Yeah?
Sorry, do you know what page this example is on by any chance?
Oh, yes.
I just want to follow along with the notes.
Yeah, this is on page 4 of the notes.
Okay. Yeah. Oh, got it. Okay. Sorry.
Yeah, equation 8 is
okay.
This equation.
Thank you.
Yeah, you're welcome. Okay, so without invoking any theorem, let's just say we had this idea. Like we think when we zoom in, we don't know Taylor's theorem. We just know that when you zoom in enough, things look like a line. So let's figure out what line it is. So how should we choose this line so that in some sense it best approximates the function near this point? So our constraint is that we would like to match the value of f and the slope of f at x equals x naught. Okay. And so now we're going to use those two constraints that we want our approximate function to match the value and the slope at that particular chosen point. We're going to use those two constraints to find m and b, so we have our line is defined. Okay, so so these constraints give two equations. So first one, so we want to match the value. So the value, we have f of x naught is equal to some value f naught. So you just plug in, I'm not going to plug in 4 and get a numerical answer, but you can plug the number 4 in, calculate the sine squared plus the other terms. You get some specific number. I'm calling that number f naught. And for the slope, so we know the interpretation from calculus that the first derivative of the function is just the slope of the tangent line of the function at that particular point. And so for the slope, we want to match f prime of x naught is equal to g prime of x naught. So we want to take these two equations and use them to figure out what is M and what is B, so we can define our best fit line. And so this one here, the value equation, this is kind of as good as we're going to do. We just know the function has some value. But for the slope, we can take the derivative of our approximate relation here. So we say we have g of x equals mx plus b. So g prime of x is just equal to m. So at x naught, we would like g prime of x naught to equal f prime of x naught. So we want the derivatives of the two functions only at the point x naught to be the same value, so that they have the same slope at this particular point. If you're going for a linear approximation, you can't really do much better than that. So a linear function has two parameters, the slope and the y-intercept. We here have two constraints, the value and the slope. And if you wanted to match more properties like second derivatives, higher derivatives, you'd need to include a more complicated model than just a line. Okay, so right away, these two equations tell us that so g prime equals m, and g prime also equals f prime. So right away we have a formula that m has to equal f prime of x naught, where this is a derivative we would compute by hand. So f prime of x naught is equal to you have 2 times sine of x naught times cosine. Taking the next derivative, minus 10 e to the minus x naught, and the last term is 2 log x plus x naught plus 1 divided by 1 plus x naught, right? And so this works out to be some concrete number. If you plug in x naught equals 4, you'll get some specific number for it, and that'll tell us what our value of m is. And so for b, we can now take our two equations and combine them. So let's see. So we've already found m. So to find b, we have our equation here, g of x equals mx plus b. We now know m. But at x naught, we want g equal f. So we can write f of x naught, which we've just called f naught, is equal to m times x naught plus b. So when we plug x naught into this linear formula, we want the value of that linear formula to equal the value of the function we started with. Okay, and so this allows us to solve. We can just solve this for b. We know m, we know x naught, we know f naught. If we're given the function, we can compute that. So we can just solve this for b. It's really simple. So we get b just equals f naught minus m x naught. Okay, so these are our two parameters for our line. And so now we can write down what's our final linear approximation. So our model linear function is g of x is equal to m times x plus b, I should write down the formula for m, sorry. So m we said was f prime of x naught. So this is our m times x plus b, which is f naught minus m again, f prime of x naught times x naught. So this was our m, and this is our b. So again, so we haven't used any theorem. All we've done was we said we want a line, we took some derivatives and made used our two constraints. We want to match the value and want to match the slope. And just based on those two constraints, this is the only line that we can choose. And we can rearrange this. So let's just get rid of some of these decorations here. So we have f prime of x naught times x plus f of x naught. This is what we've been calling f naught minus f prime of x naught times x naught. So our three terms. But two of them have this same coefficient, f prime of x naught. So we can factor this. So I'm just going to rewrite this as, I'm going to write this term first, f of x naught. And then factoring the f prime out of these two, we get plus f prime of x naught times x minus x naught. And so this could already be recognizable, as this is actually exactly the first order Taylor formula. So if we just define, just to make sure that everything is notationally consistent, so defining the notation delta x is defined as x minus x naught. So delta x measures, so we have this base point x naught, and delta x just measures how far are we wandering away from x naught as we try to model this function. Well then, we get here, so from this we can, from delta x equals x minus x naught, we can rewrite x is equal to x naught plus delta x. And so our formula becomes g of x naught plus delta x is equal to f prime of x naught plus, f prime, just f of x naught plus f prime of x naught times delta x. And so if you look back in your notes, this is exactly the way that we defined the Taylor series. So I think I erased it, but it was exactly the f of, so g approximates f, so as we say, our function evaluated at x naught plus delta x is equal to the function's value at x naught plus a term proportional to the derivative of the function, the slope at x naught, times the distance we've moved, delta x. And so this is exactly, so this is the result. The exact same as Taylor's theorem to first order in delta x. And so I just like this example because it gives a nice practical interpretation to what this Taylor's series really is. And it's just sort of a quick way to calculate what are the linear approximations, or if you go to higher order approximations to any function about some specific point. And so whether you do it from a modeling perspective and just try to match a line to the curve, or whether you apply the theorem directly, you get to the same result. And so the interpretation is the same. When we zoom in and zoom in and zoom in, any function looks like a straight line, and what that straight line is determined by Taylor's theorem. Okay, any questions on that? Yeah?
So is this like a derivation for the first order Taylor series? What we've done?
Not really. So it's, I would say it's like a physicist's derivation. So it's not like a real derivation, because if you wanted to actually, so this was meant as an illustration to say that if you take a first order Taylor series, the answer you get is the exact same as if you just tried to match a line with those two constraints, that you match the value and you match the slope. If you wanted to do a derivation of the full Taylor series formula, what you need to control is the accuracy approximation. So what we've said here is, if you want to fit a line with these two constraints, this is the line, and we calculated it. But what we haven't done is give any formula for how accurate is that approximation. And the full derivation, or the full proof of Taylor's theorem shows that the error actually decays like delta x squared. So it has some control on the accuracy of the approximation. You say, for sure, with theorem level confidence, we know that if your delta x is a certain small size, then the error can be no greater than some bound. And so the full derivation is more technical. This is more of a sort of intuitive illustration of the consistency.
Okay.
Yeah. Any other questions? Okay, great. Okay, so that's it for Taylor's theorem in one dimension. And so now we're going to move on to some vector calculus concepts. And that's going to tie back in to Taylor's theorem as well. Okay. So this part is vector calculus. In lots of areas of physics, electromagnetism, heavily in fluid mechanics, other areas, anytime you're dealing with multiple dimensions of space, it tends to be true that the equations of physics are written in a vectorized structure. Meaning when you write the equations down, and maybe there's three components of force, for example, an x component, y component, z component, it tends to be that physics is nice in this way, where the equations can usually be written in some form where the vector structure is natural, as opposed to writing it out like an x component, y component, z component, all separately. Actually, it's interesting, in the past, physicists, or all working scientists, and by the past I mean like say the 1800s, they had a lot of the physical ideas that we have now, but they didn't necessarily have the notation that we had. So one time I was looking through a book on electromagnetism that was written by Maxwell, who's an old physicist who worked on electromagnetism. And the book is just impossible to read because like every equation is written out in x, y, z components. So every equation becomes three components. A single equation is like pages long. But now we have this really nice notation. And so the formalism that we use makes it a lot easier to handle a lot of the math that comes up in physics problems. So the way that derivatives are, the first derivative, are collected up into vector form is called the gradient. Can you put your hand up if you've seen the gradient operator before? Okay, so those who have not will see it for sure in vector calculus. Probably once you, I guess I could ask what you're covering so far. It was the first week. So
yeah, it's
curves
like in review and like the dot product.
Okay, so so you will definitely cover this gradient. So the vector form of the first derivative operator is called the gradient. It is denoted by an upside down triangle with a little vector symbol above. And so, I mentioned when I say an operator, are people comfortable with the idea of what an operator is? Yeah? Yeah. So it's just it's anything like, so like d by dx is an operator. You give it a function, it gives you a new function. You give it, so the operator d by dx, for example, think of this as a sort of machine. You put in a function f, and it produces a function f prime of x. So the gradient is an operator like this. So it takes functions and gives you functions back. So the gradient operator is defined as the vector that contains the three partial derivatives with respect to the three coordinate directions. You can define this either in 2D, which would just be d by dx and d by dy, or in 3D, which is more common, with dx, dy, and dz. And so for any function f, we'll call it a scalar function. For any scalar function, f of x, y, and z, which would also often write just f of vector x, then the gradient of f is a vector. So f starts out as a scalar, but then because the operator has vector structure, when you take the gradient of a function, it goes from being a scalar function to being a vector. And the vector is the vector of partial derivatives so it's just the first element, the x component is the x partial derivative of f, the y component of this vector is the y partial derivative, and the z component is, of course, the z partial derivative. Okay, so this thing shows up all the time in physics, basically for the reason that we often care about first derivatives, and the nature of physical laws is such that they tend to show up in this vectorized format. So instead of seeing d by dx in fluid mechanics equations, you often see gradient, which means that you're tracking the rates of change in all three spatial directions. And this is going to be very important, especially for the pressure gradient force. So we're going to talk in a few classes exactly what is pressure and how are those forces defined. We probably all have heard of it casually, And so when there's a gradient in the pressure field, that results in forces that are acting on the fluid. Okay, so how do we interpret? So this is the mathematical definition. So if I gave you anything on homework, you do this, just give you some function, you can calculate these vectors. That's one of the exercises. But what is the interpretation? So beyond just it being a first derivative of some kind, what's the interpretation? So interpretation of the gradient of a function. So the gradient, which is actually first here, is orthogonal or normal or perpendicular to contour lines of F. So by contour lines, I mean curves along which F equals a constant. And so this is probably easiest to see by example. So let's consider the function here. F of x and y, so we're just going to do 2 dimensions for now, is equal to x squared plus y squared. So this function looks like the definition of a circle. So if f was if it was x squared plus y squared equals r squared, that would be the typical definition of a circle. And so when we say the contour lines, what we mean are the various lines where f equals constant. So we could say for our, what's the contour line for f equals 1? That would be the curve defined by x squared plus y squared equals 1. We could say f equals 2. That would be x squared plus y squared equals 2, and so on. And because of the specific formula that we've chosen, these are all the definitions of different circles. So our contour lines look like this. So here's 1 minus 1. And then to make things easier on myself, I'm going to put 4 here instead of 2. That way the radius is 2. So 2 x. And so these concentric circles that sort of form a bullseye are the curves on which f is constant. So if you were imagining yourself in the xy plane, just wandering around, if you were an ant or something, and you're walking along this circle, and you're measuring what's the value of f as you move around, you find that the value doesn't change. And so you get one value on this circle, you'll get a smaller value on this circle, but the set of concentric circles are the set of contour lines. Also, it's called level surfaces, depending on the context of that particular function. And what I mean when I say that the gradient is orthogonal or normal to these contour lines is that if we go around, we'll do this example, if we go around and calculate what the gradient is, the gradient vector always points normal to these surfaces. So it's all, and it turns out also it's pointed radially outward. So we'll explain why it's outward and also why it's normal. So, so let's call this the proof. Not really a super rigorous proof. But if we move, so we imagine that we take this perspective that we're wandering around in the xy plane, and we're measuring our value of f as we wander around. So if we move in the xy plane by a small amount, I'll say a small displacement, delta x, the change, so we can imagine we have some baseline point, we'll call that point x naught, and then we're going to take a little excursion, delta x, and move around that point x naught. If we move in the xy plane by a small displacement delta x relative to x naught, the change in f is, I'll go to the next board. So in one dimension, so this is just a little aside. So if we have a function, just f of x, if we say, so Taylor's theorem tells us that if we wander a little bit relative to x naught, our new value of our function is this. So we have the background point plus our little change. And so what we often write is we write df. So this is the change, the infinitesimal change in the function f that occurs because we move a distance delta x. That change in the function is just equal to delta x times df dx at x naught. Okay. So if we do this in 2 dimensions instead, we get a very similar formula. So the change in f is now in 2D, df is equal to delta x times partial f partial x, evaluated at x naught, y naught, plus delta y times partial f partial y, evaluated at x naught, y naught. So we move a little distance, delta x vector, which has a delta x component and a delta y component in the xy plane. And then the function is going to change. df, the incremental change in the function, is equal to how much we move in the 2 directions, delta x times delta y, times the slope of the function in those two directions. But we can rewrite this. So if we wanted to, we could rewrite this as delta x delta y, and then take the dot product with df dx and df dy, where this is evaluated at x naught, y naught. So we can define this quantity here. This is our infinitesimal displacement. And so we can write that as delta x vector, just defining some notation. And then the dot product, but this vector here is the vector where the x component is the partial x derivative, and the y component is the partial y derivative. So this actually happens to be exactly the gradient. So if we want to know how is the function changing as we move around, the thing that tells us that is, first of all, how far we went. Obviously, the farther you go, the more the function is going to change generally. And also the slope of the function, which is measured by this vector gradient. And now because we're moving in 2 dimensions, it's no longer sort of a scalar formula, it's a vectorized formula involving the vector displacement and the sort of vector first derivative. Okay. So, if we now assume that instead of, let's say, now suppose we choose delta x such that we are moving along a contour surface. So we're moving along a contour line of f. So that means that our dx, here's our circle, and so our dx is something like this, or something like that. Our delta x is the tangent vector of one of these contour lines. So I'll say here, i.e. delta x is proportional, is along a tangent vector. So in that case, we know, so df is equal to delta x, dotted with our gradient, and that has to be equal to 0. And the reason it's 0 is because we've just defined our motion to be along the contour line. lines. So contour lines are defined by the fact that f doesn't change as you move along them. So if you move along the direction of one of these curves, then your function, by definition of the curve, has to not change. And so, what this means, what this means is that the dot product of our gradient operator we just defined and our tangent vector to our curve, the dot product has to be 0. And if the dot product is 0, that just means that they're orthogonal. That's the definition. So if here's our delta x, then we know that the gradient of f has to be orthogonal to that, meaning it has to either look like this or it has to look like that. Those are the two options. And I'm just drawing this one as dashed because that's not the correct solution. It turns out that the gradient of f is orthogonal to the contour lines, and also it always points toward the direction in which f is increasing. So it always points towards higher values of the function. This shows gradient of f was orthogonal to contour lines. Okay, so next we'll talk about this idea that the gradient, this is still in the interpretation, that the gradient points toward higher values. The direction of the gradient points toward higher values of f, as opposed to lower values. So we can see that. So again, consider a displacement delta x. Then our change in the function df is delta x dot the gradient. And now it's clear that if you so let's think about this equation here, and let's now imagine we're not necessarily moving along a contour line; we're moving any arbitrary direction. So if you wanted to, the change in the function is equal to the dot product of these two vectors, our displacement vector multiplied by our gradient. So if we were choosing the displacement, and we wanted to maximize df, we wanted to maximize the change in the function so that's positive, so that f is incrementing by some value. Can anyone tell me how should we choose this delta x? Based on this formula. So just assume gradient of f as some given vector, and you now want to choose delta x so that you make this as big as possible. How do we do that? So, as a hint, so suppose we have some particular vector, let's call this v1. And now I want to look at all the vectors of, let's say, of unit size. Obviously, you could make this df very, very large by taking delta x huge. If it's thousands of kilometers, this could be big. But assuming delta x stays small, you can't play with the size of it, you can just play with the direction. So we have some vector that's given. So this is like the v1, that's like our gradient. And then now, there's a whole bunch of other vectors in the plane that we could choose. So of this like wheel of vectors, which one is going to make the dot product between that vector and v1 the biggest?
The one parallel to it.
Parallel, right? And so why is that in a word? Like, so can you give like one more sentence on like why is that the appropriate choice?
Well, because if you're multiplying the vectors together, we would assume the dot product, right?
Yeah.
So then if you're dotting them together, then the projection would be 0 if it's perpendicular, and as you get closer and closer then.
Right, so this vector here would be the worst, right? If you chose that one or that one, you get 0 dot product. And so the two best that give you the most, so usually the dot product, right, A dot B equals AB cos theta. And so cos theta is maximized, it's the largest value is +1, smallest value, or the most negative value is -1. So what we want is for this cos theta to equal +1, which means theta equals 0. So we want the angle between the two vectors here to be 0. So that means that this one just lines up with that one. So the point is, in the case where we have now the v1 vector is this gradient vector, we want to pick our delta x such that it's lined up with our gradient vector, and that way we'll get the biggest dot product. And the dot product gives us the change in the function. So, to maximize df, we want to choose delta x so that it is aligned parallel to gradient of f. So we could write delta x is equal to a constant, some numerical constant, times the gradient of f. And just based on this geometrical argument, trying out all the vectors, the one that's going to give you the most projection is the one that's already in the direction you have. So then we can say that this vector is just proportional. It does not have the same magnitude, but it has the same direction as the gradient of f. And so then, df is equal to a gradient of f dot gradient of f, which is just equal to our constant times the magnitude squared of that particular vector, the gradient of f. And we choose here, A is going to be positive because we want the line, we want the two vectors to be parallel rather than anti-parallel. And then so we get that in the end, this is a positive value at our constant A times our gradient squared, and that gives us a positive number. And you can sort of convince yourself geometrically that if we chose any other vector, we wouldn't have as high projections. This dot product might still be positive, but it won't be maximized. And so this shows that gradient of f points in the direction of steepest increase, or fastest increase, of f of xy. Okay, so that's the interpretation. So we have any arbitrary function. Maybe it looks like a circle, maybe it looks different. You can draw contour lines that show the level sets or the curves along which that curve is that function is constant, and then the gradient always points normal to those curves and always points to the higher values of the function. So you can imagine, and there are actually algorithms that do this. If you were searching for the highest value of a function, a sensible thing to do would be compute the gradient and then move in the direction that gradient tells you it increases. If you kind of keep doing that, you'll eventually sniff out some high values. You could be caught in a local maximum, for example. This is actually called the method, when you make an algorithm out of this to find the highest points of the function, it's called the method of steepest descent. And it's just based on this simple idea of the gradient. And if you are involved at all in the machine learning neural network type revolution that's going on right now, you may have heard of stochastic gradient descent. It's one of the key methods that people use to train neural networks. And it's based on the same exact idea. The usage of the word gradient is the same. You're essentially calculating the gradient of a neural network model with respect to the weights and biases. And so this type of operator shows up not only everywhere through physics, but also in every area of math, including machine learning. Okay, so that's the interpretation of the gradient. So now we're going to use that gradient idea to extend Taylor's theorem from 1D into multiple things. So this section is called Taylor's theorem in more than one. So in 1D, you just rewrite that result. Taylor's theorem says that f of x naught plus delta x is equal to f of x naught plus delta x times df dx divided by x naught. I'm just going to leave out the error terms here, so I guess I'll put my approximate there. Okay, so when we go into 2D, the exact same logic applies. And if you wanted to go back and do a very similar example to what we did with the line, and we sort of figured what's the best fit line to the curve at a particular point, matching the value and the slope, you could do the same thing in 2 dimensions, but then you would have a situation where instead of our function being a curve, our function defines a surface, and then instead of fitting a line, you would fit a plane. So you're approximating some kind of curved surface by a plane. So let's say, for example, we have here x, y, z, and then we have some cool looking 3D surface. Then at a particular point, you might say the plane that both matches the value of this surface at that point, and then also matches both slopes. So now you're going to have a slope in the x direction and a slope in the y direction. And there's a plane that satisfies those 3 things. Matches the value and matches the 2 slopes. And that would look something like that. Hard to draw 3D functions, but something like that. So we can fit with a plane rather than fit with a line. And so the mathematical formula is very similar. So now, suppose we have a function f of x and y. So near, we'll call this now f of vector x argument. So vector x equals xy. So near the point x naught equals x naught y naught, we have f of x naught plus delta x and y naught plus delta y. So again, we're looking near a base point, x naught, y naught, and we're going to allow ourselves to wander in the plane at distance x naught, delta x in the x direction, delta y in the y direction. That's approximately equal to f of x naught, y naught, plus, and now here is our first order, but in 2 dimensions, Taylor series. And we get 2 terms, well, 3 terms total. So we get the base point, our base point, plus the amount we move in the x direction multiplied by the slope in the x direction, plus another term we didn't have before, and it's delta y, how much we move in the y direction, multiplied by the slope in the y direction. And so this is our Taylor formula in 2 dimensions, and we can rewrite that using sort of slipper notation as x naught plus f of x naught plus delta x vector equals f of x naught plus, and then we can see again, we've had the same situation where we have delta x and delta y, which we can group into the vector delta x, delta y. And then if we take the dot product with the vector that has the 2 partial derivatives, we get this kind of structure. And so we can write that as f of x naught plus delta x dotted with the gradient of f, where the gradient of f is computed at vector x naught. So this here is how Taylor's theorem is then extended into two dimensions. And so it's exactly the same as in 1 dimension. It's just that you pick up this extra term that corresponds, it has the same exact form, the delta of the displacement, multiplied by the partial derivative in that direction. And we can combine it, and this sort of points out how the gradient starts to arise really naturally. That if we're looking near this point x naught, We want to know if we move in an arbitrary direction, delta x, a small delta x near this base point, what's our new value of f going to be? And Taylor's theorem tells us that the value is going to be similar to the original value, fx naught, but plus a correction that's given by delta x, the displacement vector, the small displacement we moved, multiplied by a dot product with the gradient of that function. And so that's how Taylor's theorem works in 2 dimensions. And a particular case that we're going to, and you can imagine if we did it in 3 dimensions, you would have a third term here, delta z times partial f partial z. And I'm just going to take a moment to do a specific special case that's going to come up concretely when we start deriving the fluid mechanics equations, which is really sort of the full version of Taylor's theorem that we'll mostly use for fluids. So a particularly important special case is Taylor's theorem. And when I say special case, I just mean it's important to note it's not special in any way. It is, all the different dimensionalities are the same. There's just one that we're going to use a lot. Is Taylor's theorem in 3D plus time. So we have 3 spatial dimensions, x, y, z, and then also t. So just going based on this pattern, so following the pattern, we can write, we have f of x, y, z, and t, which we often write as f of x and t. So we're generally, in this course, going to separate space and time out. We're going to treat x vector as the x, y, z vector variable, and then time separately, just as t. Sometimes it's useful to wrap all of them together in sort of more numerical mathematical calculations, or if relativity is important, but for us, that's neither of those are true. So near a point x naught and a time t naught, we could write f of x naught plus delta x, and separately t naught plus delta t. We can follow our recipe here. So we have in 2 dimensions, we have 2 terms. Now we're going to have 4 terms, x, y, z, and t. So we'll have here f of x naught, t naught, plus delta x, partial f, partial x, plus delta y, partial f, partial y, plus delta z, partial f, partial z, plus delta t, partial f, partial t. These are all evaluated at x naught, t naught. And so we can do the same thing as before, and we can collect up these 3 different terms into a vector structure. So this is equal to f(x naught, t naught) plus the vector delta x, delta y, delta z, dotted with df dx, df dy, df dz. And we usually, again, separate out the spatial terms from the time part of the equation. That's just conventional. And then we can write this in our last step as f of x naught, t naught plus delta x dotted with gradient of f evaluated at x naught and t naught plus the partial time derivative delta t first, delta t, and the partial time derivative evaluated at x naught, t naught. Okay, and so this is now our full version of Taylor's theorem, 3 spatial dimensions plus time. And so they always have the same structure, but just, I think it's worth it to introduce it piece by piece because the formula could look a little bit gnarly and complicated seeing it for the first time, even though really it's just a sort of direct generalization of the 1D Taylor's theorem, that line fitting that we did. So we're going to apply this equation over and over to derive the physical laws of fluid mechanics. And on the first assignment, there's an explicit calculation question where you just calculate this, and this gives an approximation. So again, this approximates the function f near the base point x naught and the base time t naught, assuming we're wandering a little bit in space and time according to delta x and delta t. And this is the first order Taylor approximation, which is all we'll need. We don't really need higher order in 3 plus 1, 3 space plus 1 time dimension. Because this is an approximation, it will have some error. So if as delta x and delta t go to 0, if we go right to the base point, this becomes infinitely accurate. But for any finite delta x and delta t, even if they're small, there's some error here. And so in the first homework, you just work this out for specific. I give you a function f, you calculate the terms, and then you make a Python plot of the error of this, just showing, generally speaking, as you wander further from the base point, the accuracy of your approximation gets less and less. And so you just make a plot of that. Okay. So, that's it for Taylor's theorem. Okay, so the next part of the review is on differential equations. Can you put your hand up if you've had a course called differential equations? Okay. So everybody has some familiarity. So generally, the Navier-Stokes equation, which we're going to be using a lot, we're going to derive it. It's a particular type of differential equation called a nonlinear partial differential equation. But all differential equations are kind of the same in some ways. And so this section is just sort of about what's the point of a differential equation? How do you use it? So generally, laws of physics are mathematically represented as differential equations. And these are equations involving one or more derivatives of a given function. Usually, and we're trying to find that function. So it involves one or more derivatives of a function we are trying to find. So maybe the most famous example is Newton's second law. So Newton's second law is F equals ma. And this is a differential equation because A is the second time derivative of the position of a particle. So as a differential equation, we would often write this as the second derivative of the position is equal to 1 over m times the force. Okay. So, so usually what happens in physics is we have some kind of law, like Newton's second law, or a law of maybe gravity forces. We know something about the forces F, maybe gravitational interaction, electrical interaction. We're going to deal with things like pressure forces and frictional forces and stuff like that. You have some knowledge of F that's given to you by the physics of the problem, and then your task is you want to solve this. So the goal is to solve this equation for the trajectory x of t. And so if we are able to do that, so if we're able to solve this and get the trajectory x of t, what that tells us is that this equation has allowed us now to do a prediction. So that's really the essence of differential equations, is that they express the content of physical laws, And also they allow us to do prediction. So when you solve the differential equation, you get out the trajectory of solution for the rest of time. And that allows you to predict where exactly will the particle be at some future time. And so when we study the Navier-Stokes equation, we're going to have an equation for the velocity field, and maybe also the temperature, density, pressure, stuff like that. And it will allow us to predict at all future times what the fluid will be doing. And so this is obviously a central goal of physics, right? So things like numerical weather prediction, this is the whole point. You want to know what the weather is going to be like in 2 days. How they do it is that there's some kind of pretty complicated differential equation. They put it on a computer. I'm going to explain how you do that. And then they tell you, well, based on this model, the wind is going to be whatever, the temperature is going to be whatever. And so it's obviously very interesting from a practical perspective to solve these differential equations, because it's the fundamental essence of doing any kind of prediction. Okay, so next time, so we're out of time now, so next time I'm going to talk about a specific example, a very easy example, just a falling particle. Then the challenge that we'll talk about is that most of the time when you take a course on differential equations, you're mostly exposed to lots and lots of different tricks, like oh, if this is a Bernoulli type equation, then you do it this way. If it's separable, you do it that way. That's all very useful. But an impediment that comes up essentially always is that the average differential equation that you will encounter in the wild, so you have some real research program, you're analyzing a real shift architecture, or you're doing some realistic problem with internal Earth structure or whatever. The equations that you get are essentially never going to be of those special types. They'll never be separable, they'll never be Bernoulli or whatever. And so we have to come up with methods. If we want to do this prediction problem, we have to come up with methods to deal with differential equations that are given to us by physics that allow us to do the prediction to solve the equation without relying on these tricks that only work in special cases. And so the answer to that is you use a computer. And so next time we're going to talk about numerical solutions to differential equations. And then I think that will then cover the last problem on the homework. So I'm going to go ahead and post the first homework tomorrow. It's not due for like another 2 weeks. And then I think by Tuesday you should have enough lecture material to cover all of the topics that are on that homework. Okay, that's it for today. I'll see everybody Tuesday. Have a great weekend. And as always, just let me know if you have any questions. Okay, bye.
Thank you.
Thank you.